Hello and welcome to Optimizing Mass Spec Metabolomics Applications presented by Biocompare and sponsored by Merck KGaA Darmstadt, Germany. My name is Tamlin Oliver. I'm the managing editor at Biocompare and I'll be the moderator for this webinar. The effective use of metabolomics in basic and translational research has game-changing potential. Unfortunately, the lack of standards often impedes the realization of this potential. This webinar will explain why standards are important, discuss best practices on how to create custom metabolomics libraries, and explain how to optimize mass spec analytical protocols. Before we get started, though, I'd like to remind everyone that we hold a live Q&A session at the end of the presentation. You can submit a question at any time using the Q&A box on your screen. Now let me introduce today's speaker. Dr. Felice de Jong has extensive experience in metabolomics and life science research. She served as a technical manager at Roche and is founding president of Signal Aldrich Australia. Before founding Iroa Technologies, she developed metabolomics business and marketing strategies at Metabolon. Dr. de Jong, welcome to the webinar.
Hello, and thank you all very much for joining, and thank you for the introduction. As part of this presentation, I will discuss the use of metabolomics standards for mass spectrometry and show you how to create a library using authentic standards together with a software tool. As for the agenda, I'll start with a detailed description of the Mass Spectrometry Metabolite Library of Standards, or MSMLS, and what's in the kit, uses of MSMLS, and then give an overview of the compounds provided and their descriptors. And this will be followed by the MSMLS workflow, including sample preparation and LC-MS analysis. The majority of the presentation will focus on a software tool called MSMLS Discovery that's provided with the kit, what the requirements are to run the software, the setup process, and then finally data analysis and library building. All right, so what is MSMLS? The kit contains 7 96-well plates, and these are deep well plates with a maximum volume of 1.2 milliliters. As standard, these plates are alphanumerically coded, rows A through H, columns 1 through 12, containing 96 compounds per plate. 5 micrograms of dried compound is supplied in each well, 1 compound per well. The compounds are high purity, small biochemical molecules with a molecular weight generally less than 1,000 Daltons. A plate map for all the plates is provided, which I'll talk about a little later, and also provided is the software tool Discovery and a user manual for the software in the kit. The MSMLS kit provides over 600 authentic small biochemical molecules in an easy-to-use format. And with 5 micrograms, there's enough material for multiple injections for the purpose of building a physical mass spectral library using the conditions that are normally employed in a mass spec lab. And while, as you know, many mass spectral libraries are available commercially and can help identify compounds within a data set, there's really no substitute for generating your own library using your own parameters and authentic standards. So the most common use for the create mass spectral libraries using accurate mass over charge ratio and retention times, which are used to identify compounds in biological samples. These standards can also be used to help determine the sensitivity and limit of detection of various mass spectrometry methods. The compounds provided largely represent primary metabolism, and therefore they're ideally suited to build libraries used to identify compounds for metabolic profiling. And as noted in the slide, MSMLS can also be used for cellular assays, and there's a larger library version now available which supplies 1 milligram per compound per well. So there are 619 unique compounds, actually 634 in total, as 18 compounds have been intentionally represented more than once for quality control purposes. And these duplicated compounds have different DL forms, chirality, or salt forms, and also have different Cas numbers. And as all 619 compounds cover primary metabolism, they're very useful in metabolomics studies. Listed here are some of the classes of compounds that are in the library, including carboxylic acids, amino acids, amines, nucleotides, vitamins, sugars, fatty acids, and lipids. A plate map covering all 7 plates is provided in an Excel format specifying the exact location, the plate number, row, and column location of each single authentic standard. Also provided is the SMILES, or Simplified Molecular Input Line Entry System formula, the chemical formula, and the neutral monoisotopic mass for each compound. The plate map is a very valuable resource as it also provides a series of useful compound and identifiers and descriptors, including the CAS, or Chemical Abstract Service ID, CHEBI, which is the Chemical Entities of Biological Interest ID, that's put out by the European Molecular Biology Laboratory. The KEG ID, which is the Kyoto Encyclopedia of Genes and Genomes, collected by Kyoto University, and that also includes metabolite chemical compound information. The HMDB, or the Human Metabolome Database ID, and that was created by the Human Metabolome Project, and it's a database of small molecule metabolites found in the human body. The METLIN ID, which is a repository of metabolite information, as well as tandem mass spectrometry data, maintained at the Scripps Institute, and PubChem, which is a database of chemical molecules maintained by the National Center for Biotechnology Information, which is part of the NIH. And for each compound, the Sigma Aldrich, now Millipore Sigma, compound name, catalog number, and URL are provided. So this next slide here shows a schematic of the MSMLS workflow. The first samples are created and then analyzed using liquid chromatography and mass spectrometry, and then finally data analysis. And I'll discuss all of these individually. So to create samples, 5 micrograms dried material of each compound are provided, which is really plenty for multiple injections, and to build libraries for different acquisition methods that are employed in the lab. And the product information sheet provides instructions for sample preparation, but we recommend using methanol to begin solubilization and then diluting as required with water, and suggest a final 5% methanol solution. Water here is necessary to ensure solubilization of the more polar compounds. And for plates 6 and 7, which contain more lipid-like compounds, we recommend using a ratio of 1 to 1 to 0.3 chloroform methanol and water. The entire library may be examined in great detail by performing individual injections for each of the unique compounds. But rather than 600 individual injections, the library may also be analyzed as simple multiplex injections. So if individual rows are pooled, and this is done for every plate, then the entire collection may be analyzed in only 56 injections of simple mixtures. So generally, the compounds of every row have distinct molecular weights and can be multiplexed by pooling all the compounds in a single row for injection. However, sometimes the plate map will change due to the availability of compounds, and so the plate map should be consulted before pooling compounds to make sure that the compounds can be individually detected. But if higher resolution mass spec is employed, less than 50 ppm, then this usually is not an issue at all. So there's no best chromatography, and of course this is dependent upon the instrumentation available. There's no single recommended mass spec model and or protocol. The library was designed to help you tailor your own system and support your ability to build a library using authentic compounds under the source and chromatographic conditions available in each laboratory. For example, multiple liquid chromatography methods such as reverse phase liquid chromatography and hydrophilic liquid interaction chromatography, HELIC, can be used, and perhaps different LC columns employed, in addition to positive and negative ionization modes. Many researchers who have used the MSMLS preferred a basic C18 column run in both positive and negative mode, and then a HELIC or diamond hydride column is often employed to further separate the very water-soluble compounds. Several methods can be applied to ensure the analysis of all standards provided, because they're all, chemically diverse. Following LC-MS analysis, the data files should be converted to centroided MZXML format prior to uploading to MSMLS discovery software, as these files are much smaller and process much faster and accurately than profile data. And both MS and MSMS files are supported by the discovery software. Okay, great. Now, let's move to the software side of the presentation. So to employ discovery, Microsoft Windows 7 or higher, 64-bit, with a minimum of 8 GB memory is required, and for faster data processing, 16 GB memory is needed. The latest version of Java must be installed and callable. And while discovery is intuitive, a comprehensive user guide is provided. So the remainder of the presentation will focus on the discovery workflow, namely setting up the project, assigning search parameters, assigning compounds to samples, and then loading the respective MS data files. And then once this is completed, the compound search can be performed, and then the results reviewed and curated, and then finally the library will be ready for export. And if multiple libraries are made using different acquisition methods, these can all be combined to form one larger library. Okay, so at project startup, a window pops up, and that's shown here on the left side of the slide. And this allows the creation of a new project or to open an existing one. Here, we simply, specify username and email address. And then once loaded, the program will store that information. To initiate a new project, we click on the Create New Project button, which is the left button here, and that will bring up the first page of a new product wizard shown on the right side of the slide. Under Project class, in this part of the slide, select Library Generation from the drop-down menu. Specify the name and the description of the experiment. So let's say for the purposes of this demonstration, we're going to examine the compounds in Plate 1. So here we might name the project Plate 1. Now we choose a project home directory for where all the project information will be stored. And then click the Next button to move to the method definition screen. So the raw data acquisition method definition screen is this next panel, and that will pop up shown here on the left. And this is where the name, description, polarity, and MS depth is specified for each method. So for example, we'll name the method LC positive for data collected using positive polarity. There are two MS depth levels. Select level 1 for MS and level 2 for MSMLS data. And use the Add Method button, which is the green plus sign, to add specified method to the project. And it will show up in the Define Methods table just below it. So here, each analysis method that you've used to collect raw data is added. So in this project example, we would add all methods that were used to collect raw data for Plate 1. And you have the opportunity to edit method information and add and delete existing methods later in the program as well. And when you're finished adding all the methods, click Next, move to the sample definition screen, and that's shown here on the right of the slide. For the sake of simplicity, the sample definition wizard is limited to specifying the common name prefix and the number of samples. So in this example, let's assume we've pulled each row in Plate 1. So here we specify 8 samples, representing the 8 rows, A through H, in Plate 1 that we're going to examine. Now, once the number of samples are added, click the Finish and Close Wizard button at the bottom. So now this Multiplex Designer panel will pop up. And this is where we're going to finish defining the experimental design. The first thing you'll notice is a series of icons on the top left. And these are all described in the user manual. On the top row, from left to right, there are buttons to create a new project, open an existing project, download the project, and there's an MS calculator for molecular formula generation. Next is an ATOC list generator, and this allows the user to edit the ATOC list. And I'll discuss this in more detail in a few minutes. And then there's a library database editor. And then, so once the libraries are generated, this is used to manage the compound libraries. And using this tool allows editing of all the library data, including name, molecular formula, descriptors, and retention time. There's a knife and fork icon, and this is the program preferences icon. And this is used to set the search parameters, and I'll also describe this in detail shortly. There's a help window, and then the last icon in this row is Save the Project and Exit button. The next row of icons below include buttons to edit the name, project description, and user information. That's that pencil with the green check mark. And then next we could add multiple samples or then add a single sample. The red X is to delete selected samples. And the magnifying glass is used to find library compounds in the samples. And this is the button to run the program after the whole setup is completed. And then the next button is to show the library panel, and this is where you can export libraries. And then after that, let's see, is the button to show library merging panel. And this is where we can merge libraries. And again, I'll describe that a little bit more in detail. So the 8 samples created earlier are now listed in the multiplex samples table, which is panel B shown here. So now we want to tell the program which plate compounds are in the samples. Now I'll describe the individual panels A through E later, but first, since there are different MSMLS library versions available, we must first identify the mass spectrometry library and compounds that were used to create the data files. So to do this, we're going to click the Edit Program Preferences, which is that knife and fork icon on the window bar at the top. And then this Set Preferences window will pop up. And this is where the search preferences are set. Parameters are specified separately for each mode. And as indicated by the title of this window, we are setting preferences for LC negative. And if there were additional acquisition modes used for plate 1, then these would have to be set separately. So here we select the Create Library tab. And that is the tab fourth over, which is identified using a green circle. And from the pull-down menu associated with MSMLS library, you select the correct library. And if you're not sure which library version you have, you can use your plate map to verify the compounds in the sample composition, which I'll show you later. Okay, so once you've selected the correct library, this screen may be used to modify the other program parameters. And you'll see it's already has numbers already filled in, and these default settings are a good place to start, and then you can tune them as needed. I'm sure many of you are already familiar with many of these settings. I'll give you an overview of these parameters, and these are also fully defined in the user guide. The minimum peak intensity, this is the minimum intensity setting for the base peak. And this depends, of course, on the data. And once the raw data files are loaded, it makes sense to browse through the scans to estimate noise. The minimum fragments intensity, this is the minimum intensity for fragments. The default is set at 10%, and that's 10% of the minimal intensity for the base peak. The next is the minimum hits per compound. We recommend setting this for at least 2 or 3 when running library generation, as the same M over Z may occur in the same sample more than once. And then peak width limits. This is the minimum and maximum allowed width of the chromatographic peak. And the minimum should allow the fit of 3 to 4 MS scans for the peak to be reliable. The filter width is the width of the smoothing filter used to define the chromatographic peak borders. And this is used for better definition of peak start and end in noisy data. The maximal charge is the largest charge to consider when looking for mass spectral features. The minimum number of ions and adduct, we recommend setting this to at least 2 to exclude junk peaks. Maximum isotope pattern deviation percent, we recommend 10% for library generation. Search for fragments. When this parameter is checked, fragments will be included in the search. Fragment lookup cutoff. This is defined as the percent intensity of the major adduct. This should not be set too low, as you're going to end up with a lot of small peaks. So the suggested setting here is between 10 and 25%, and then adjust empirically. Fragments retention time tolerance. We suggest here using the same value as set for the minimal peak width above, as fragments are expected, of course, to collude with major adducts. And the minimum signal to noise for fragments, we recommend setting this to 2 or 3 initially, and then again adjusting empirically as needed. So once any of these preferences are modified, the program will save the new settings. I wanted to show you this set adducts, and this was also an icon on the multiplex designer panel near the knife and fork preferences button. And the adduct list editor is a very handy editor. It allows the user to control which adducts to include in the search by checking these individual boxes in the left column of the window. The green plus sign button allows you to define a new adduct not listed in the table, although it's a very comprehensive list. And the M+ add button allows you to edit a selected adduct, and then the red X button allows the removal of an adduct. Okay, so now we're back to the multiplex sample assignment window. And we've set now the preferences and the adducts for the search. So now that the program knows which library was used to generate the data files, we need to assign the correct compounds to each of the multiplex samples. So let's use the example I mentioned before, our test example. We're working with plate 1, and that we've made samples from multiplex rows A through H. In other words, all of the compounds from row A were pulled, and all the compounds from row B were pulled, etc., for all the rows. And for the purposes of the discussion, the pulled rows A through H represent samples 1 through 8. So first, we highlight the compound multiplex sample number 1 in window B. And then look down to the compound plate map window D. As you can see, it mirrors each 96-well plate, rows A through H, columns 1 through 12. And in our test example, we're working on plate 1. So plate 1 is selected from the scroll down window, and that's circled here in green. And compound multiplex number 1 is represented by row A. So just below the circle, we can either individually select compounds by checking each box in row A, 1 through 12, or simply by checking A in the first column. All of these boxes in that row will be automatically selected. So now we would click on the green plus sign to the right of the circle, and the selected compounds will be linked to compound multiplex sample number 1. And table C, the selected sample composition panel, will be populated with all 12 compounds from row A that we've selected. Now, once populated in table C, you'll see the compound name, formula, the exact mass, and descriptors. And many of these descriptors are clickable. And if you highlight a specific compound, such as the beta NAD highlighted here, the window E in the bottom right of the slide will be populated to show the structure of the compound together with the compound descriptors. So now is a good time to verify that you're using the correct library. So simply look at the Excel plate map provided with your library, plate 1, row A, and compare it to these 12 compounds listed in window C to make sure that they're the same and that you've selected the correct library in Program Preferences. Now, if you need to change the compounds that were assigned to the samples, this can be easily done. Compounds can be individually removed by selecting the compound in window C and then clicking the red X to the right of that green circle, or the entire list of compounds for a highlighted sample can be removed by clicking the sweeping broom icon. Okay, so next we need to load the MS data files, which were generated from the analysis of the multiplex samples. And these will be loaded into panel A on the left. Okay, so now we're going to load the raw data. When the Load Raw Data button is highlighted, and that's identified here by the green circle, the far left A panel is now used to load the data. And here, the LC negative data tab has been selected, which has a green arrow pointed to it. So it's ready now for the LC negative data files. So data files can be either loaded by dragging the data files from the directory where you have them stored, and you can see here 8 files being dragged in, or by clicking the green plus sign, the Add Raw Data Files button on the toolbar seen under the green circle, where if you click that button, a new window will pop up. And that's shown in panel B. And here you'll be able to navigate to your directory containing your raw data and select the desired files. During file import, a task monitor screen is activated, and I've shown that here in panel C. And this shows the operation progress, so you'll know when the process has started and finished. So this procedure is repeated to add all the data files for each acquisition method. So for our example, next we might load the LC positive data. And once all the data files are loaded, now we need to assign the data files to the correct samples. But before that, I wanted to point out that once the data files are loaded, they can be examined in detail. So in the Data Analysis panel, which I've circled here in green, you can click on any of the data files in the left panel and select an individual scan. And then as an example shown here are MS and MSMLS scans in the lower windows. And this has been done for sample 1B, and this happens to be scan number 2111 in LC-MS negative mode. Okay, now we're back to the we're back to the multiplex sample assignment window. So to assign the correct data files to the samples, we click on the Assign Files to Samples button, and that's identified here by the green circle. and then use the pull-down menus below it to assign the data files that were loaded for each acquisition mode, LC negative and LC positive, to each compound multiplex sample. So for example, for compound multiplex sample 1, both negative and positive plate 1A data files are assigned. Sample 2, the row B data files are assigned, etc. So when this is done, the compounds and their uploaded data files are both assigned to the correct samples. Now we can finally use the discovery software program to search for compounds, adducts, and fragments in all of the data files for plate 1. To start the program search, we click on the magnifying glass icon that the green arrow is pointing to on the top of that figure. So after several minutes, this data analysis screen will be populated. And by default, all of the compounds found in the data files for all analytical modes will be listed in alphabetical order, shown in panel A here. The compound names are color-coded, red for positive mode, blue for negative mode. Clicking on a compound in the tree, as we've done here for adenine, will bring up the following information in the corresponding panels. So panel B shows the extracted ion chromatograms for base peaks for the detected adducts for adenine. Panel C is the mass spectrum of detective adducts in a table format with mass and relative intensity. And the errors shown are comparative to theoretical values. Panel D is the average mass spectrum plot, MS1, across the compound peak, and the detected adducts are shown in red. Now, if I jump over to the MS2 scan data tab, circled here in green, we're going to see in panel A the MSMLS M over Z in intensity values table, if there are any available for the MS1 adduct base peak. And shown in panel B is the MSMLS plot, again, if data is available for MSMLS. Okay, so the next step is to carefully review all of the data and curate it if necessary. So as you know, a good thing to do is look for good peak shape, good peak intensity, and compare, retention time across positive and negative modes. And data can be removed for results where the automatic algorithm has failed simply by clicking on any bin or any individual adduct in the tree and selecting, you right-click and select the delete command. So after the curation process is completed, the library may be exported by clicking on the Export Library button that the green arrow is pointing to at the top of the figure here. So the library can be exported in tab-delimited CSV plain format, plain text format, or Agilent Chemical Exchange Chef format. Export is possible for all analytical modes simultaneously, and the data can be saved separately for each mode or combined for all methods. If multiple libraries have been generated, say for each plate, These can be combined and exported using this library merger panel shown in this slide. The Merge Existing Libraries window represents a series of icons in the top of the left slide. So in the top left of this slide, from left to right, you can either append libraries with a green plus sign, remove any selected appended libraries using that sweeping broom, export libraries, or export a filtered list of libraries. Upon closing the discovery program, the entire project will be saved, as well as all of your raw data files, your project preferences, and any exported libraries that you've created. And these will all be available in the home project directory and can be reopened at any time. Well, I hope this WebEx tutorial has provided a good overview of MSMLS and the software tool discovery. And thank you very much for joining me today.
And thank you, Felice, for that overview. It was very informative. Before we begin the Q&A today, I want to introduce a special guest who will help Felice answer some questions. Sasha Raskind is a specialist in the analysis of complex biological data and the development of integrated database-driven software applications. Sasha works with end users to ascertain scientific and technical specifications and implement complex algorithms for scientific data analysis. Welcome, Sasha. I think it'd be a great addition to answer these questions because we do have a lot of them. So if you have a question, please submit them now. We have plenty of time to answer questions. So let's get started. Felice, the first question is for you. Which are the most adequate assurance controls to the analyzer?
To the most adequate controls to the analyzer. Not sure if I understand that question. If the analyzer means the software, that would be in the preferences toolbox, which I showed you during the presentation. Here, the user can set all search parameters, and very specifically, I showed you the expert mode preferences, which listed, I believe there was about 10 or more options to select, and we're always available for to expand on any of these parameters, and so I welcome getting further questions on this topic.
All right, well, I'm going to throw the next question to Sasha. Sasha, welcome. The question for you is, for data acquisition, is it possible to acquire data using switching mode, positive and negative mode simultaneously, question mark? MSMLS Discovery is able to handle this type of data, question mark? Sasha, are you with us?
So I don't know whether,
all right,
and I apologize if there might be some kind of a technical issue with Sasha's phone or something, but I can answer that question.
Oh, beautiful. Thank you.
If that's appropriate. So the current Discovery version does not support mixed polarity data. That's something that could be easily programmed, but we don't have that right now. So right now we suggest just running positive mode first and then negative mode. Thank you.
All right, Felice, here's a couple more questions for you. Do some grows contain isomers?
Yes, certainly. there will be isomers, probably not in the same row, but we try to avoid having isomers in the same row because obviously they can't be separated very easily. So, and that's why I mentioned that, it's always good to consult the plate map, and if you see isomers in the same row, you probably wouldn't want to multiplex them together.
All right, Felice, here's another question for you. Can you comment on the stability of the library compounds in the solid state and methanol solution? Is there stability data for multiple freeze-thaw cycles?
Yes, yes, there is, and that's a very good question. So we suggest that, so the library itself, when you receive it, we recommend keeping it at minus 80 degrees, and it should be fine for a number of years in that state in a solid form. Now, once you solubilize them, if that's stored at minus 20, that also should be fine for months. But really, what we would suggest to do is to avoid freeze thaw, and by when you're after solubilization, aliquoting amounts into separate tubes and storing them at minus 20 or even better minus 80. And as I say, that in methanol even they'll be fine for months and months. So thank you. That was a very good question.
All right, Felice, I have another question for Sasha, but if he's not here with us, I'll throw this one at you. Sasha? No? All right, so Felice, it's yours. Can the software be used to create custom libraries from derivatized metabolites?
Oh, another good question. That's something, that's a feature that we're going to build soon in subsequent software versions, and that is it's certainly in our pipeline. I can reiterate that by saying, what we really would like to do is have the software, used for any compounds, for, any standards that you would, have. So, yes, that's in the pipeline.
All right, Felice, the only other question I was going to ask you seems to be a duplicate, just someone wanting more reassurance on those isomers. That must be a topic of particular concern, but you already addressed that, so I apologize. That is it. Thank you very much for joining us today. Unfortunately, that's all the time we have. Thank you very much, Felice, and sorry Sasha couldn't be with us today, but we appreciate that you were here and shared your knowledge with us. We also have a special thank you to Merck KGaA Darmstadt, Germany for sponsoring today's event. This webinar will be available on demand shortly. You can watch it again or share it with colleagues by going to biocompare.com. Thank you for attending today's webinar, and we look forward to seeing you at our next event.